Hello everybody and welcome. Today we're going to be taking a look at collision between circles and lines. It could also be spheres and planes in 3 dimensions, but we're just going to be looking at the 2-dimensional case. And if you need the 3-dimensional solution to this problem, it should be pretty self-explanatory to extend it upwards. But anyways, so take a look at this circle. Let's imagine now that we are in a world with gravity and the circle is falling down. At the present moment, if there's no collision between the circle and the line, the circle is going to fall down, and it's going to pass directly through this line here. I don't know about you, but I live on planet Earth in the real world, and that's usually not how things happen. If we want to make our simulation more realistic, we would have the ball fall down here, and it would run into this thing, and it might slide off, it might bounce off. That behavior can be different depending on how you decide to handle a collision between the objects. But at the root of the problem is we need to figure out when this circle is colliding with this line here. So as it moves down further, you might end up with a circle in a state like this. Obviously, this is an illegal state if we're trying to simulate the real world here. A circle can't be existing inside of a line like that. So we need to have some sort of collision resolution that knows how to fix it and bring the circle to a valid state for the world like this, perhaps. So let's take a look at our line here. How are we going to solve this problem? Now, a line is 2 points. Let's call these points P1 and P2. And now I'm going to move everything up here just so we can make it a little easier on ourselves. Actually, maybe make it a bit farther down here. But let's take our line here. This is our line P1, P2. So we need a couple vectors that are going to help us out here. We need a normal vector, first of all, and this vector is pretty important. It's going to stick out from the wall, basically. It's important that it's a unit vector, and this is going to tell us where the collision should reject the wall. So if I have a circle here, then it's easier to then have it's going to be rejected in the direction of the normal. Not super important for now, but we need to have a normal wall that points perpendicular to the wall or the line here. And we also need a couple vectors. So these vectors are going to reside on P1 and P2, and they're going to be pointing towards the center. Now, these are actually residing on P1 and P2, but I'm just going to draw them above it just for the sake of clarity here. So let's call this V1, and we'll call this N, and then this is going to be V2. So now what we need to do is how do we tell if the ball is actually colliding here? First thing we need to figure out is the ball or the circle within these sort of imaginary lines here. Is it in here as opposed to out here? This whole area, if the circle is within here, we know that the circle is a candidate for colliding with the wall, because say even if it was out here, it would not be colliding with the wall, even though that if this line were extended, it would be colliding. However, it's not, because it's outside of these 2 lines here. So how do we tell if the circle is within these 2 lines here? Well, it's easier than you think, actually. We just need to use the vector dot product, and the vector dot product is very useful in game physics. It's quite magical, actually, and it can do lots of things for us with relatively little computational power, since it's just multiplication and addition. So what we need to do is let's say our circle is here, and we need to figure out if it's between these 2 lines. What we have to do is we make 2 new vectors. Let's get a new color here, and we need to make 2 or actually just 1 vector. So we need to extend a vector from P1 to the center of the circle. Now, what we're going to do is we're going to take the dot product of V1 of, okay, let's call this vector, this is going to be V3. And what we do is we take the dot product V1 dot v3. Now, if this dot product is greater than 0, then we know that the angle between these two vectors, right, the angle between v1 and v3, we know that this angle, let's say this angle theta, we know that this angle is, well, it's between 0 and 9, it's between negative 90 and 90 degrees, right? And that would constitute it being in front of this imaginary plane here, right? So that's how we check that. We need to check if the dot product between v1 and v3 is greater than 0. And now we actually just need to do the exact same thing over here, right? We just extend a vector from p2 up to the center of the circle. It's called v4, right? Now we just need to check the dot product of v2 with v4. We say v2 dot v4 is greater than 0. By the same logic, if the angle between these two vectors, v2 and v4, if it's between negative 90 and 90 degrees, then we know that it's in front of this plane here, right? So that's the first two tests for our collision detection, right? But the problem is the circle could be over here, over here. These are obviously not colliding, right? The way that we want to check for this, right? I'm going to go ahead and move over here. The way we want to check. All right, and we're back. The other condition that we need to check is, so we have our line here, and we have our circle, and let's assume now that we've made it past that test, we know that it's between these two lines, right? So we need to make the final test, right? Which now this is where the normal comes into play. So the normal is sticking out from the wall, and it's right here. And let's say the circle is over here, right? Now what we need to do, and the circle has a center. Now what we need to do is pretty similar to the other problem. Let me just grab this color. Oh, we're on the wrong layer. Pretty similar to the last problem. We're gonna extend a vector from here, and this vector, let's call v5. We are going to dot this vector with the normal. We're gonna dot this vector with a normal. So now let's take. So now we do v5 dot n, and since n is a normal vector, what this is going to give us is it's going to project v5 onto this normal vector, right? And so what we'll get is this little tiny distance here. It might be bigger though. And so this distance is going to be the component of v5, which lies upon the normal. And so, so let's go ahead and sort of draw that here. This here is v. This is v5 dot normal right here. That little tiny section there. And so if this is greater than the radius, or if it's less than the radius of the sphere, then we know that if it's less than the radius, then we know that this circle is colliding. Because if it was greater than the radius, that would mean it was over here, and if it's less than the radius, that means this. Basically, what this does is it extends a line from perpendicular to the wall to the center of the circle. And so, if that line is greater, if it's greater than the radius, the length of that line is greater than the radius, then we know that the circle is not colliding. And likewise, if it's less than the radius, we know that it is colliding. So that's our full algorithm for telling if the circle is colliding with the line here. Now let's go ahead and take a look at a way that we could resolve this. All right, so we've got our circle and it's colliding with the line here. Now let's just say we're ignoring like momentum and that the ball's not bouncing or anything. We're not doing anything crazy. All that we need to do is move the ball up so that it's it's up here. You know, we just need to move the ball so that it's up here, and it's no longer in a state of colliding. Now, the way we need to, how we do that is we just need to see this, there's a difference here, there's a distance here between the line and the edge of the circle. Now, I'm going to call that dr. Now, this is the distance that we need to move it along the axis of the normal in order to resolve the collision here. Now, there's a simple way that we can get this distance here. Since we took the dot product of this, we took this dot product of this vector, I think it was v5. We took the dot product of v5 with the normal. That gave us this distance here. Now, let's just call this distance v5 dot normal. We're going to call that, I'm just going to call it dot. So now we have our circle, and and this length here is dot. This is dr. Now, we want to obtain dr. So dr is equal to, notice there's something special here. This point here is the center of the circle, and this point here is on the edge of the circle. So we know that the total distance here is the radius of the circle. So we know that the radius of the circle is equal to both elements here. It's equal to dr plus dot. Now, if we rearrange, now we know dot, we know radius, and we're trying to find dr. So let's rearrange this equation. We're going to get dr equals radius minus dot. Now we got dr is equal to radius minus dot, and we're almost done. Now all we need to do is move the sphere by dr units along the normal axis. And the way we do that is we can say, the circle's position, right, plus equals the dr, the distance to move it, times let's do this symbol because we're working with vectors here, dr times the normal vector. And that's about it. That's a very simple collision resolution that we can do using this detection algorithm. And that's going to be it for this video. I think I might do a video explaining how we can implement this in code. But for now, thanks for watching, and I'll see you in the next one.